Now that we've removed the unnecessary pieces from our fractured geom and updated our constraints and built some proxies via convex decompose, let's start setting up our initial RBD sims. Now I've object merged in that cached destruction asset here with all of the fractures and proxies and constraints. And to work with that, we're going to need to drop in an RBD unpack to split out those various items. And we're not going to deal with the fractured geometry directly. We're just going to sim the proxies. And for this week, we're going to ignore the constraints. We'll deal with those some more next week. So I'm just going to drop in a null node and connect that to the third output of the RBD unpack. Call this null proxies, and we'll display that. And for these initial sims, to speed things up, I'm going to call out some of those small pieces with our measure fracture sub. So we'll turn off the bounding box size computation because our proxies already have that data saved and we don't need to recalculate it. But then we can still use that size filter. So flip that to bounding box, connect our proxies to that. Maybe we'll try a size threshold of 0.1 and see what that looks like. It looks like that's deleting a decent number of pieces, and we can drop in another null to view the leftover geometry. I'll just call this sim pieces and display that. And this gives us about 4,500 of our original 40,000 pieces. So that'll be pretty decent for a starting point for our sims. Now to build this initial simulation, we'll create a DOPNet to contain the sim. And we should also make sure that our timeline is set properly. In this class with this animation, we're focusing on the time range from 985 to 1150. You can change that in your animation settings. Make sure the start and end is correct. And on the DOPNet's simulation tab, make sure that start frame is set to 985. Now we can bring our fractured geometry into the DOPNet by connecting it to those DOPNet inputs, and that's totally fine to do it that way. And we can also just tell the objects in the DOPNet to refer to null nodes in our scene to pull in the geometry that way as well. So we'll just start out doing it that way. So if you dive inside the DOPNet, we're going to use the bullet solver for our RBD sims. So if you just type in bullet solver and create that, and we'll connect the bullet solver to the output. And right now, this solver is just a computational step. This doesn't have any actual geometry to run the solve on. So we have to give this some sort of input to solve. So we'll use an RBD packed object and connect that to our bullet solver. And this RBD packed object, as implied by the name, requires that the input be actual packed geometry. You can't put raw polys into this solver. And we'll point this SOP path parameter to those sim pieces that we just set up above. So you can type in ... to jump up 2 levels to get to where we've started setting up our sim pieces, and then we can pull in that sim pieces null. Now to go through some of these properties available on this RBD packed object. This RBD packed object can create either active objects or static, or it can be animated static objects or deforming, as indicated by all of these options here. For this scene, we're just going to use active objects, although we can later override some of those pieces to be static, which we will look at shortly. And on these lower tabs here, usually we don't have to worry about these position, rotation, velocity, and angular velocity options. Those will give you some initial options for the overall pieces. But if you want to specify initial velocity, you will typically want to set that per piece out in SOPs out here rather than just specifying some velocity inside the DOPNet on this RBD packed object. because this will apply the same velocity to all the pieces we're bringing in, and that's rarely useful. On the Bullet Data tab, this Show Guide Geometry option is extremely useful. So if you turn that on, then it will create these convex hull visualizations around each of our fracture pieces. Now you'll notice that these convex hulls are pretty big, and some of them don't look like they're conforming very well to the pieces that we're importing. So if you remember, each of our convex decomposed pieces might be made up of several different chunks to form one packed piece of geometry. And if we just leave the defaults on our RBD packed object node, then it's going to create one big convex hull collider for each piece of geo, even if that piece has been internally decomposed into a few sections. So in order to get the colliders to respect the actual segmented convex decomposition, you'll have to turn on this Create Convex Hull per set of connected primitives option. It's a very important one. Otherwise, if you don't turn that on, then we don't really get all the benefits of doing a convex decompose in the first place. So when you turn that on, you'll see that now our convex hulls perfectly match what we've set up with our convex decompose. Now on the geometry representation, you can use other types. You can use concave collision objects, or boxes, or capsules, cylinder, etc. And almost all the time we want to leave this on convex hulls. That's what Bullet deals with most efficiently, and pretty much all the time I'll just leave it on that. There are some other cases where I've used perhaps boxes to represent cell phones in one case, or something like that. And I have used concave for the occasional static objects. For example, if there's a terrain with a lot of concavity, I will sometimes just use concave for that one piece of collider geometry, since it's not too slow if it's just on one piece. But certainly for a big building like this, you want to always be using convex hull collisions. Now the collision padding will expand or shrink these collider convex hulls, and often these defaults are totally fine for that. One case where you might need to change that is if you're working at a pretty small scale and you have a ton of tiny objects, and the generated convex hulls don't give you a very good representation, then sometimes you could reduce that padding and shrink amount to get the convex hulls to conform better to really tiny pieces. But for this scale, I think these values will be okay for now. Moving on to the physical tab, you can control some more properties of the pieces. You can control the density, which will affect the mass. The rotational stiffness, I don't use all the time. I use that probably pretty rarely. The ones I use the most are bounce and friction. And one of the things you want to be sure to avoid in an RBD sim is an overly bouncy simulation. So I typically set this to a really low value to start, because if it's too bouncy, that's one of the major things that can really make a sim look amateur and unrealistic. And the friction really depends on your particular case. That's kind of up to your own artistic judgment. And for now, I'll leave that at the default value of 1. Now let's go back to our Bullet Data tab, turn off the guide geometry for our collision objects, and we're not quite ready to simulate yet, because right now, our sim will do nothing. The bullet solver doesn't give us any automatic gravity or anything like that, so we need to go ahead and add a gravity force here, and we can drop that in after the bullet solver. And just so we have something to collide with, we can create a ground as well. So you can just type in ground to create that ground plane object. And to get our active pieces to collide with that, all we have to do is merge that into our DOPNet stream here. So just drop in a merge node, and typically we'll use this setting. It's the default on the merge that says that left inputs affect right inputs. That means that the connection order on the merge matters. You can see here the active pieces are going into the left of the collider pieces, but we want the collider pieces to affect the active ones, not vice versa. So on that merge, you can just hit the little up arrow on that ground plane to put those in the correct order so that the collider is affecting the active objects. Now with all of that set up, we can zoom out a little bit so that we can see where it collides with the ground, and we'll go to our flipbook options, and we can leave this set to the entire frame range if you want, or for this test you can limit it to a partial range, maybe set the end to 1080. We can leave this on flipbook to mplay, and you can leave everything else default if you'd like. Maybe I'll expand this a little bit and hit start to see what this first sim looks like. Now my flipbook is finished, and you can see it's a bit clipped off at the bottom and the top compared to the viewport. If you want to include your entire viewport image, you could, underneath the size tab, try turning off the explicit resolution or turning off that crop out view mask overlay option. Although whenever we're doing our flipbooks from the camera view, you should always make sure to leave this on because we don't want to be biased by things that are off screen. But in any case, this is fine for our initial RBD sim, and you can see everything is collapsing straight down. Not too exciting yet, but we will improve on this as we move forward.